Hey folks, so we're continuing section P.2. Let me encourage you again. I mean, if you're just watching this video and just waiting for me to do it, you're missing out on a lot of opportunity here. So you should be trying these problems on your own and then watching the video to kind of see if things are coming out right or wrong. I'll post an answer key to this at the end, so maybe you don't even need to watch the video. You can just look at the answer key and see how you did. But just as a reminder, you should be trying to push yourself to do a lot of pausing and a lot of trying on your own. Okay, so we're looking at natural log. So natural log of the quantity x minus 2 is less than 0 if and only if these things are true. Well, we don't know any of that until we start to look at what this function looks like, especially after a transformation. So let's do just what we did on the front here. Basically, this is saying, when is this function negative? That's saying where on the graph of this function are the y values below the x-axis? Where are they negative? So I need to sketch it. Well, I'm going to start off by sketching the parent function and then applying any transformations to get the function that we want. So you tell me. All right, pause it, go. All right, let's see how you did. So you should be sketching the parent function first, which is clearly natural log. So the natural log graph is like all the log graphs, kind of something like that. And then we're going to apply any shifts. A couple things to remember is you have an asymptote and you have an intercept of 1. That's for the parent function, an x-intercept of 1. Okay, so what is our transformation? Well, it looks just like we only moved in the x direction. So we got a minus 2 next to x. So that's going to be a horizontal shift. And remember, it always does the opposite of what it says for x, of plus 2. So I'm going to take my curve, I'm going to shift it plus 2. That's going to become my new asymptote. And then here's my 1. So no stretch strengths, reflections. All we did was a translation. So which x values, which x values correspond to y values that are negative? So it looks like everything from here to here is going to have some negatives. So we would write this up a little bit fancy. This is how we would say this in an advanced math course like we're in right now. So we want to know when the function is less than 0. So natural log of x minus 2 is less than 0 for all, upside down capital A means for all x that are an element of this sort of fancy, it looks like a C with a little line in the middle. That means element of. And then what interval is this? What x values does this cover? This covers all the numbers from all the x values from 2 to 3, but not including the endpoints, because this is an asymptote. And then here, what's that y value at 3? It's 0, which is not less than 0. It'd have to be less than or equal to. So I don't want to include the ends of that interval, so I'm going to use an open. Oops. Nice save there, right? The interval from 2 to 3 not included. So then down below they used what's called set notation. So which one of these is from 2 to 3 is part C. So then we would box in this. There's our answer. If f of x equals e to the x, which of the following lines is an asymptote? Oh, that's an easy one. You should be able to do this one. Pause it if you haven't yet. So what do I need to look at? I need to know what e to the x looks like as a graph. So I'm going to sketch that first. E to the x are like all exponential functions. Start asymptotic, launch off to infinity. There's the graph of f of x equals e to the x. And the question is, where's the asymptote? So there's only one asymptote. It's the x-axis, but what's the equation for the x-axis? It's the equation. So this x-axis hits every x number, but only hits the y number of 0. So that x-axis of y equals 0 would be our asymptote. If the solutions of my function if the solutions of f of x equals 0 are negative 1 and 2. So let's just stop and try to understand what does this mean. Let's review what this word solutions translates to in math. It translates into roots, translates into the word zeros, translates into the word x-intercepts. All right, all those things are read the same in math. So it means that our graph, whatever our function is doing, it has a y value. Our function values are equal to 0 at negative 1 and at positive 2. So if we're looking at a picture of this, at negative 1 and at positive 2, our graph has zeros. Our graph has a y value, remember f means y value, has a y value of 0 at negative 1 and 2. Negative 1 and 2, these are the zeros. But then what happens to our transformation? Our transformation comes along, and it's going to move those zeros. So first of all, this divide by 2 is getting attached to the x by multiply. So if it's attached to x, this is a horizontal stretch by how much? I always like to say stretch. You might say compress by 1/2, but it's actually, I think of it as a stretch. I always think of them as stretches, and then remember, because it's attached to x, you do the inverse of what it says. So this negative 1 is going to get twice as far away to negative 2, and this 2 is going to get twice as far away to 4. So my new zeros, my new solutions, my new roots, my new x-intercepts are going to be at negative 2 and positive 4. Let me prove it to you. Let me just prove it to you. So I'm going to make a function. I already did a little bit of legwork on this, so I know I'm going to expand x minus x plus 1, x plus 1, and x plus 1 and x minus 2. It's going to be x squared minus 2 plus 1 is minus x minus 2. So x squared, subtract x, subtract 2. I'm going to take my windows down to the 5s so that we can see it better. All right, so look at what happened here. Where are my zeros? My zeros are occurring at negative 1 and positive 2, right? Now I'm going to transform my function. That means I'm going to take the x and replace it with x over 2. I'm going to go to my equation now. I'm going to replace x. Let's make a new one. X gets replaced with x over 2 squared minus x gets replaced with x over 2 and then minus 2 at the end. Now when I graph this, it should be the same picture except stretched in the x direction by 2. So look at now, where are my y-intercepts? My x-intercepts, sorry, where are my zeros? One of them is at negative 2. The other one is at positive 4. So hopefully that proves to you that I'm not crazy and that those zeros would get stretched just like the function gets stretched in the x direction. Okay, this one is kind of weird just because it's a notational thing, but don't overreact to this kind of stuff. This is how math people talk, and we've got to start to get used to that language. So if f of x1 plus f of x2 is equal to f of x1 plus x2 for all numbers, so you're talking about the whole real number set, which could be the function of f? Well, I don't know. I don't know which one of these would do that. So what I'm going to do is I'm going to check them and test them, see what works. In other words, I'm going to see what f of x1 plus f of x2 is in this equation, and I'm going to see if f of x1 plus x2 is in this equation, and if they're the same thing, then I did it right. I know it's right. So let's try one. Let's do this. So what's f of x1 plus f of x2? Well, f of x1 would mean I'm going to take the x's out and replace them with x1. So that would be x1 plus 1 plus, I'm going to change the colors to make this maybe easier to see. So f of x1 plus f of x2 is equal to, okay, f of x1 means I take this function and I replace x with x1. So that would become x sub 1 plus 1 plus, now f of x2, that means I'm going to replace x with x2, x sub 2 plus 1. Now let's clean this up. Well, x1 and x2 are different values, so they're going to be the same, x1 plus x2, but I can add the orange one and the green one together to get a plus 2 at the end. Now let's see if f of x1 plus x2 is the same thing. So that would look like f of x1 plus x2 equals, so now I'm taking out x and I'm replacing with x1 plus x2. So we would get x1 plus x2 and then plus 1. Are these the same thing? No. So now we can eliminate, we can kill off one of these. So we can kill off, let's kill off A. Now let's try the same thing for part B. You try it, see how you do. Okay, so I'm trying to compare, hopefully you paused and gave this thing a whirl. Trying to compare f of x1 plus f of x2. So f of x1 plus f of x2, I already ran out of room, would be equal to, so 2x1 plus 2x2. Then let's see what would happen if we change this to f of x1 plus x2. So now I'm taking my x out and I'm replacing it with x1 plus x2. So that would be 2 times this x now gets replaced with x1 plus x2. Are these the same thing? Absolutely. We would then distribute. Hey, we didn't have to go very far on this one. Yay. These two end up to be the same thing. So then now we can box in this function has this characteristic. Which of the following equations has y equals 1 as an asymptote? Well, start sketching them. I mean, there's no really other way to do this without starting to try to draw a picture of what's going on. So natural log, if you haven't paused yet, you should pause and sketch a picture of all these. Okay, let's see how you did. Natural log looks like this. Does this have an asymptote of y equals 1? Y equals 1 hits the y-axis at 1? Definitely not. I can eliminate that one. Okay, sine. What does the sine curve look like? Be careful. Sine and cosine look a lot alike, but they're not the same. The way I remember it is I plug in 0. What's sine of 0? I go to my unit circle. I draw a little unit circle. Over here, this is the point 1 comma 0. So sine is the y, so that's 0. So sine starts at 0 and then it cycles through. This side is going to do the same thing. Does this graph have any asymptotes? No, we probably didn't even need to sketch it to remember that it doesn't have any asymptotes. This is intimidating. This is intimidating. This isn't too bad. This is the graph of e to the x. Okay, what's the graph of e to the anything? E to the, that's the exponential function, so that's going to look something like this. Right? But there's a transformation that's a reflect connected to the x value, so that's going to reflect our picture across the x's. So the negative x's are going to become the positives are going to become the negatives, and we get an actual graph that looks like this. Now, does this have an asymptote? Absolutely. But what's the asymptote's equation y equals 0, not y equals 1. So, all right. So we're down to 50-50, and this happens a lot in this class. You want to narrow down your choices, and if you have to guess at this point, you have to guess. But what I'm hoping that you realize is that you remember from pre-calculus and from, we'll just leave it at that with pre-calculus, that we can figure out the HAs based on the leading term on the front and the leading term on the bottom. So this graph is essentially, it's not really this picture, but at the ends, as you head off towards the infinities, this is the same as x squared over x, which is the graph of x. So this, in the infinities, this graph kind of looks like the graph of just plain old x, which is just a straight line. Does that have any asymptotes? No. This graph, though, turns out to be x over x, turns out to be 1. That means that we have an HA of y equals 1. Remember that back in the day? So this would have an HA of none because there's more x's on the top than on the bottom. What happens if there's more x's on the bottom than on the top? That has an HA of 0. That levels off at 0. So this is the graph that has levels off at 1, so that must be our curve that has an asymptote at 1. Oh, yeah, this is a good one. Find the function g that is finally graphed after the following sequence of transformations are applied in the order given the graph of a function. So reflected about the x, shifted down 3 units, stretched vertically by 2, reflected about the y-axis. So this is not one where you get to pick and choose. You have to go in the order that they've told us. So let's start off with the function. Actually, pause on your own. I got to keep saying it, but hopefully you'll get to the spot where you can just do this without me reminding you. Pause and try to do this on your own. Okay, we have some function. We're going to call that function f of x. We do a transformation. Our first transformation is to reflect about the x-axis. That means to flip things over the x-axis. So if you want to flip things over the x-axis, they're going to go from the top to the bottom. Who's changing there? Should be your y value. So now I want to change the y values. I want to reflect the y values. So that's going to attach a negative to my function. That's going to change my y values. Okay, my next transformation, shift down 3 units. That one's probably the easiest one. If I'm going to shift downward, I'm going to be affecting x. But it does the opposite of what no. I said that wrong. I'm not going to be affecting x. I'm going to be affecting y. So I'm going to attach it to the function. So I've got the negative from the first transformation. I've got my parent function, f of x. And then I want to shift downward. Is that same or opposite? Hopefully you said same. Now I want to do a stretch vertically by a factor of 2. So you've got to be careful here because this means that I've got to stretch everything. Because they said we have to do it in their order, this is going to stretch everything in our function. So now I'm going to take this thing and I'm going to put a 2 around everything. Negative f of x minus 3. Now I want to clean that up before we go any further. So I'm going to clean this up. I'm going to distribute that 2. I don't like the way it looks. So what would that look like? We'd have a negative 2, a negative 2 f of x. And then, man, I don't know what color I should really do this. I guess I'll do it in green again. But really that shift is getting affected by that distributing that 2 in there. Anyway, okay, our last one then. Our last move, I'm going to go like this. I wasn't supposed to use blue. I'm supposed to pick a different color. Like weird light purple. And then my last, reflect about the y-axis, so that if I'm going to reflect about the y, that means I'm going to flip across the y. So what's going to happen to these values, to these, what's going to change those? My y values won't change if I flip this way, but my x values will. So that's going to be a horizontal reflection, which means I need to attach a negative to the x. So we would have a negative 2 f of a negative x minus 6. Ah, dang it. It's supposed to be in green. Minus 6. Do we have anybody who's like that? Ooh, boo, 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 boo. Dang it, no. We don't have anybody who's like that. Where did I mess up? Where did I mess up? Yeah, why would that become a positive 6? Shift down 3 units, that'd be a subtract 3. I'm going to pause for a sec, see if I can figure this out. Well, the good news is I didn't make a calculation mistake. I made a transposing, or what's it called when you write something from somebody else's stuff. But anyway, I just wrote it wrong, so that's supposed to be a minus there. And I'll change it. So this was right, but that should be a subtract. So this is the one we want. But I got to go back and edit. This is supposed to be a subtract, not a plus. All right, let's see. Do we want to keep going here? I'm going to pause there. I'm going to pause here and let us save this video. And then we'll do one more video. I think I can do the rest of them in one video. Because I think if we stay, we could probably do it, but it'll be pretty long. All right.